Hey guys, so induction proofs with divisibility, they tend to be seen as the easiest types of induction proofs. That's what IB math students usually say. Now, I wonder if that's actually the case or these students have just not been exposed to higher level types of questions which involve, as I mentioned, induction proofs with divisibility. Now, what I have for you today is one of such. It is going to require some level of creativity towards the end. So let's get to it. Prove by mathematical induction that n cubed plus 3n squared plus 2n is divisible by 6 for all positive integers. Now, this is a perfect place to talk about the difference or the similarities between being divisible and being a multiple. If you think about numbers which are divisible by 6, for example 12 or 18 or even 6, all of these guys can be written as 6 times something, and in this case or in these cases they are 6 times 1, 6 times 2, and 6 times 3 respectively, which means that in practical terms being divisible is the same thing as being a multiple. And I'm writing this to emphasize one of the steps of our solution, which is to write n cubed plus 3n squared plus 2n as 6 times a, which is only going to show up on the third step. However, it's good to emphasize this now. But let's start with the first step, which is to write the propositional function p of n. Now, what is our p of n? We're trying to prove that n cubed plus 3n squared plus 2n is divisible by 6 for all positive integers. Now, this symbol right here means the same thing as for all. So this is what we're trying to show. Now, the second step is the base case. Given that we're talking about positive integers, we're going to start with 1. Or we're going to use 1 to prove the base case, meaning we're going to replace n by 1, and hopefully we're going to get a number which is divisible by 6 or a multiple of, which of course will happen, otherwise the exercise wouldn't exist. So we got 6, which can be represented as 6 times 1. And I wrote this to emphasize the fact that we got a number which is a multiple of 6. It's the first case right here. And you should write which is divisible by 6. On to the third step, which is the inductive hypothesis. We're going to replace our n's by k and state that this number right here is a multiple of 6 or divisible by 6. So we're going to write that this is the same as 6 times a being any positive integer. Now remember, a being 1, 2, 3, or any positive integer, when multiplied by 6 gives us a number which is a multiple of 6, which is also divisible by 6. Therefore, if we can represent k cubed plus 3k squared plus 2k as 6 times a, then we're proving that this number right here is divisible by 6. Don't forget to write that you're assuming that this is true for some positive integer k. Now let's move to the inductive step. Now the inductive step is a bit different compared to other types of induction proofs, as I mentioned in the beginning. We are still replacing the k's by k plus 1 on the left hand side of p of k. Therefore we have k plus 1 cubed plus 3 k plus 1 squared plus 2 k plus 1. And we need to prove that this is divisible by 6 or it's a multiple of 6. In order to do that, we're going to make or use some substitution based on this equation right here, that when inserted right here into our p of k plus 1 gives us a number which is divisible by 6 or a multiple of 6. Now, how are we going to prove that the number that we get is divisible by 6? Well, we're going to get to show it because we will be able to factor out a 6 from the expression. Before we begin, let's expand this as much as possible. So we have k cubed plus 3k squared plus 3k plus 1, which is the same as k plus 1 cubed, plus 3k squared plus 6k plus 3 plus 2k plus 2. Now, if we rewrite this equation as k cubed equals 6a minus 3k squared minus 2k, we get to replace it right here and simplify this a lot. So ultimately, this is what we have. There we go. Now, what can we simplify? Well, we have negative 3k squared, positive 3k squared. We have positive 2k with negative 2k. We have 6 right here, 1 plus 3 plus 2. We also have this 9k, and lastly, the 3k squared and the 6a, giving us 6a plus 3k squared plus 9k plus 6. Now, you would expect to get to this point and find something as trivial as 6 times something. You could isolate 6 from this expression, right? That's the expectation. Now, in this case, it's a little bit trickier. We don't get to factor out a 6 and clearly see the result. However, this is correct. So what are we missing? Before answering that question, let me split this into two parts. We have the 6a plus 6, which both have 6's in them, and we have 3 times k plus 3. Now, both of these terms, they have 6 on them, so we're fine. Now, we need to take care of the last one. And it doesn't appear that we got to the correct solution. But the catch is the following. If k is even, this k right here can be rewritten as 2 times some other integer. Let's call it w, okay? Now, we have a 3 times 2 over here, which makes it into a 6. So if k is even, 3k times k plus 3 is a multiple of 6. Now, what if k is odd? If k is odd, this number is odd, so we cannot do anything with it. However, the k plus 3, which shows up right here, will be even. And 3 times a non-number times an even number, given that now this guy can be rewritten as 2 times w, so an even number, this will be a multiple of 6. Now, definitely not a trivial exercise, right? You would expect a induction proof with divisibility to be just fine, to be easy, but not quite in this case, right? However, do notice that the process that was used is similar to any induction proof which involves divisibility. The difference, what made this exercise a bit harder, was the fact that we had to analyze the expression that we got in the end. We had to split it in 2 different cases. Now there we have it. Now the only thing that's left for us to do is to write the conclusion. Given that p of 1 is true and that p of k plus 1 is true whenever p of k is true for some positive integer k, then by the PMI, p of n is true for all positive integers. Make sure you share this exercise with your colleagues so you can test them whether they're actually great at induction proofs with divisibility.